Okay, so good morning, everyone. Thank you for joining the Repeat final webinar. It's a pleasure to have you here. Thank you all to all the speakers here present. They're going to talk a little bit more about the project, to all the guests that will share a little bit of the concrete cases in Austria and in Estonia. I think it's going to be a very productive webinar to close this project that has been a complete pleasure to be part of. And I think it's a very important aspect of district heating and cooling ways of decarbonizing. What are the technologies behind the decarbonization of peak heat loads? But of course, this will be talked by the speakers. They will, of course, share much more information. And I invite everyone to, if you have questions, to share your questions. They will be asked at the end during the Q&A session of this webinar. And if you have any other comments, also feel free to share, because the idea is to have actually a roundtable, some sort of back and forth between the speakers and the public. So feel free also to engage with them if you have any comments or questions. So, without further ado, I will give the floor to the first speaker. Is Lars Gulev. He's a consulting specialist, currently leading the Gulev DH advisory, working with green transition support for district heating companies and municipalities with a specific focus on strategic planning, development plans, and system integration. He's also the vice chairman of the IEA-DHC program, which funds the REPRIC project. So, Lars, the floor is all yours. Good luck.
Thank you very much, and thank you for this introduction. Then I can save some time. My presentation here will give you an introduction to what IEA is and especially what IEA DHC take care of. I will not go into details in this very interesting report because I'm sure that they will be done much better by the other participants in this webinar. I just need some time here. Okay. Yeah, patient. Yeah. The International Energy Agency, it works with governments and industries and with the focus to establish a sustainable energy future for all. Totally, the IEA have at the moment 31 member countries across the world. The target is to focus on energy security, to protect the environment, and at the same time ensure that we can have economic growth as well as engagements worldwide, and I'll come back to that later. Under this IEA, we have the IEA Technology Collaboration Program, the TCP, where we have at the moment approximately 40 individual TCPs, each of them focusing on particular technologies. The one I'm representing is the TCP for district heating and cooling, established back in 1983, and have members from in the West, Canada and US. In Europe, you will find Norway, Sweden, Finland, Estonia, Denmark, UK, Ireland, Germany, Holland, Belgium, France, Italy, Austria. And in the east, we have China and South Korea. So we can see that we are more or less covering the whole world. We have the global international research in our view, and we focus on how we can reduce cost for district heating system, both in the construction phase, but also in the operation phase. And an important part there is to improve the performance of the district heating systems. And I'll come back to that later. We work with work plans for 5 years, and at the moment we are in the plan covering the period from 2021 until 2026, where we have the principal research themes, which you can see on this slide. it's important that we improve the business cases for district heating and cooling and look in another way on consumers than we have done in the past. So today we are looking at the possibility to integrate what we call prosumers, meaning customers which parts of the year are consumers and parts of the years are producers. Then we focus, of course, on the environmental impact of district heating, look at the decarbonisation of district heating systems, and here high focus on the temperature reduction in district heating networks, because lower temperatures will increase the possibilities to include renewable local energy resources in the district heating systems. Integrating of renewable energy, and here it's not only biomass we are focusing on, it's also waste heat from industries, from data centers, etc. And it's large-scale heat pumps based on air or seawater or sewage water. So we can integrate these energy resources in the existing district heating and cooling systems. Then we also have focus on hybrid energy networks, and not at least digitalization, because that's very important to focus on how we can use these huge amounts of data we have access today, use this data not only in the operation phase of district heating systems to minimize the operation costs, but also to use data in the designing of the district heating systems, to take into account the different technologies we will have in the district heating systems in the future, where we have a system integration between the district heating sector and the power sector, using more and more electricity in the district heating sector. And this electrification means that it's necessary that we can use the electricity when it's cheap, use it in the district heating system, but also produce electricity to the grid when the electricity prices are attractive for producing electricity for the district heating companies. And then at last but not least, to improve the district heating infrastructure, looking at new concepts for piping, pumps, etc. We have in this IEA DHC TCP two legs. We have a cost and a task share leg. The cost share leg, it is what the IEA DHC started with back in 1983. And here we have projects chosen by competitive bidding and founded by the IEA DHC. So that means that the founding of this project is carried out by the IEA DHC, and the funds there, they are financed by input from the participating 14 around 14 countries in the present IEA DHC. Then we, at the beginning of this century, saw an increasing interest for what we call task sharing projects, where projects arising from suggestions by members, countries, organizations. And here the participants, they cover their own funding. We started that leg back in 2011, and I'll come back to which kind of projects there we have already finalized. So that's the task care project. It's projects developed under the IEA umbrella, and the participants, they can use the IEA logos in their presentations and in their communication of the projects. The normal cost share project, it's linked to 3 years cycle of annexes, where the process is that the country consultations they carry out to determine priority themes. That's in fact what we are doing just at the moment for the next annex, starting in 2026. Then the ExCo identifies the common priorities, and then we request for proposals later. Each annex, each compromise of 5 to 7 individual projects, depending on the actual budget we have in the IADHC. And the cost share projects, which we have finalized due to 2023, they can be found at the web page you can see here. And then you can get access to that research. At the moment, we have the Annex 14 projects are undergoing, and as mentioned, we are preparing now for with background in country consultations, the Annex 15. In this cost share project period from 2023 to 26, we have these 7 projects, very different projects, a large-scale integration of low-grade sources into district heating networks through geothermal seasonal storage and heat pumps. So here again, you can see that we have the system integration between the electricity sector and the district heating sector. Then just to go to the fourth, that's the project which will be presented today, how to cover peak loads in district heating networks with renewables, the RePeak project. Then we have another one focusing on flexibility and district heating value chain. And number 6, using electrolyzers, waste heat in district heating networks, which will be a part of the future for many district heating companies as a consequence of more and more focus on power to X and the possibility to generate green e-fuels. So a wide range of different focus areas. The task share projects, as mentioned, there the idea come from the member countries themselves, organizations in the member countries, and they can start up at any time. So the procedure is that to start up such a task share project, the idea should first be submitted to the executive committee, the EXCO, as an outline. The background for that is that in the EXCO, they want to have the deep insight in what's expected to go on in these task share projects, because the projects, they make benefit of working under this IEA umbrella. If the EXCO approved this outline, and it's normally done, the task share entires to the definition stage, and the lead country organization arrange a workshop. And then as a follow-up to this workshop, a report is made for the EXCO, and if that's approved, then the task share enters to the preparation stage, and then finally, hopefully approved by the EXCO, and then the project can start up. And it can be a project with a project time of 2 years, 3, 4, 5 years. That's 100% up to the participants in this task share project. And when it's finished, a completed report will be available at the website of the DHC, of the IADHC. The current and recent task share project is mentioned here, and you have the links so you can get directly access to them. You can see the first one, they are completed already, and then the last ones, they are in the preparing phase still. And the last ones here, they are also in the preparation phase at the moment. So very different projects with different partners, and some of them with a lot of partners. So that could be interesting for many district heating companies, many industries, many research industries to participate in this task share project. At the website, you can find the full report for detailed information about the completed projects. You can also find summary reports. You can find information about webinars, all tool to search all reports. Then you have a program brochure, and then you have major links to external sources. So the website is iadhe.org, and I can recommend, if you haven't visited that yet, that you can do it after this webinar. So why should you join this IEA DHC TSP? Yes, you should do it because it gets access to state-of-the-art for international research. You will meet global research leaders with deep knowledge. You will have help to define future research projects and priorities in cooperation with your colleagues. You can bid for future cost share projects, and you can find participant in task share projects. You have the possibility for networking with experts from different countries. And then you have the possibility for a close cooperation with the Euroheat and Power and the International District Energy Association. If that's interesting for you, I recommend that you contact the program manager at the IADHC at rgfv.org, Andre Jens. The benefits for taking part in the project is that if it's a cost share project, it's 100% financed by the IEA. For task share projects, the participants, as mentioned, they contribute for their own research efforts, and they receive additional benefits of matching research efforts from other participants. Both for the cost and for the task share projects, the final reports, they are widely read across the current membership countries and also in countries outside the IEA family. You have an opportunity to build up an international network which you can benefit in your daily work. And when I look at the project which we put focus on today, this repeat project, you can see this is a good example of cooperation between different partners and across borders between countries. The study is based on feedback from 57 district heating companies representing 15 countries and from 60 district heating experts representing 19 countries. So a huge network of experts you will have access to. For me, it was interesting to see that a part of the project is a very simple discussion of what do we mean when we talk about peak heat load. It seems that it's not 100% clear what it is for all. Maybe it's clear for the individuals, but it can be defined in many different ways. And for me, it was also very interesting to see when we talk about re-peak or renewable resources for peak load production. It was interesting to see how you in the project here compare green gas, power to heat, and thermal energy storage, where you make this comparison of the ratings of economic, infrastructure, and technical aspects. So it's not that simple to make a decision which kind of technology should be chosen for renewable peak load production. Very interesting figure, I think. So thanks for giving that to the report. So that was a quick introduction to the IEA, the IEA DHC, and the IEA DHC TSP. So if you have any questions, do not hesitate to contact the IEA or to contact me as a Danish representative. So thank you very much.
Thank you, Lars, for your presentation. And again, if you have any other questions, feel free to write below in the question box, and I will address these questions after all presentations have been done, so all the speakers can answer them. So just remember before we go to the next presentation about the project, that this webinar is being recorded and all the presentations will also be available after the end, and the recording will be available at the Eurohidden Power YouTube channel. So you can check there also if you want to rewatch some part of it. Okay, so let's go to the other presentation, which is actually about the project, the results of the project. And now there will be not only one, but five speakers that will comment about the findings and the ways of the project. And there will also be at the end some policy recommendations drafted by Euratom Power. So in this presentation now, like I said, five people. The first one to speak will be Simon Moser, he studied economics with a focus on environmental and industrial economics, and he has been working at the Energieinstitut at JKU University in Linz since 2008. We also have Anna Volkova, which is a professor of thermal engineering and head of a research group focused on district heating and district cooling. She lectures at the Tallinn Technical University. Also from Talltech, we have Hesham Ali, which is a researcher in energy technology with a strong focus on heating and cooling sector, sustainability, energy transitions, and energy efficiency. And lastly, for the project presentation, we have Robert Müllehner, also from JKU Linz, which has a bachelor in environmental and bioresources management, and has a master's degree in integrated energy management with a focus on energy technology and energy management. Lastly, to talk about the policy recommendations, uh, I have here my colleague Victoria Lienar from Your Hidden Power, which is a policy advisor and has an academic background in law and political science with expertise in climate policy and industrial emissions. So I give the floor to my colleagues to present, first with Simon.
Thank you very much, Ivan, for the introduction and Lars for giving the context to our project. Good morning from my side. Hello. Welcome to our final webinar of our RePeak project, how to cover peak heat loads in district heating networks with renewables. As mentioned before, we are one out of 7 projects funded by IADHC within the IADHC Annex 14, and we are the first or second to finish. And so this is the final webinar, which I present together with our project partners from Tallinn University of Technology and Euroheat Power. And yes, I think has all been said, so I will quickly go to the next slide and give the introduction to the project. What was the idea behind, and where do we head? So many district heating networks definitely have incorporated or are based on CO2 neutral alternatives. So that means they have kind of a base load that comes from biomass or that comes from waste heat, and therefore have made big steps to decarbonize. And on the other hand, we have seen that there is a big challenge to really fully decarbonize, which means that also peak heat loads are addressed and peak heat loads are fossil free provided. And as many of you definitely know, peak heat loads are about the capacity, about the thermal power. It's not about the quantity of the energy, which makes them a very specific challenge compared to the others, to the other options or base loads mentioned. And RePeak aims to therefore explore the status quo. So, what is the situation about defossilizing peak loads, and how do we what do we see as do we find that the experts and district heating operators see as the main options to go to renewable or CO2 neutral sources? So this was our chart, paired chart. How do we address this? So REPEAK aims to explore the status quo and ways to replace fossil peak loads with renewable energy. So how big is the challenge to decarbonize peak heat loads? What are the technical and economic options and their limitations is one thing that should be initially found out. And then we really want to address the practice and see what district heating operators are planning and also what experts think that the potential solutions could be. We have put up some hypotheses in the beginning which were based on also previous studies. And we hypothesized that peak heat load lacks a precise definition, that peak heat loads are currently mainly provided by fossil technologies. We also hypothesized that net zero provision of peak heat load is not yet in the focus at district heating operators, and that green gas is a preferred option as it is using the same technologies as today and therefore is easy to be implemented. What did we do? We had an analysis of definitions and made a taxonomy of peak heat load. We derived options to provide peak heat load and also looked at the technical and economic feasibility there. And finally, and probably the main element from the time and budget perspective of the project is to identify the status of peak heat loads today and the expectation of its transition towards net zero. And herewith I hand over to Anna, please.
Thank you very much. Glad to see you all in our REPEAK project final webinar, and I will speak about taxonomy of peak heat load. And actually, this was large part of our research, and we started with it because when we started to investigate this topic, peak heat load, we understood that actually, like, there is no available structured and complex analysis of this topic. And we decided to present the result of our analysis in the form of taxonomy. And here you can see QR code with interactive tool for like literature review and definitions and classifications related to peak heat load, and link which will be available in presentation can be used to future for understanding of this term and this idea. And we had taxonomy with different aspects related to peak heat load. And first aspect is definition, which can be considered as a simple question, but in reality it was not so simple. So we investigated what definition there are for peak heat load and district heating, and actually most of definition available are related to buildings or to electricity power topic, and not so much to district heating topic. But actually, yes, we included in our report different available text definitions related to peak heat load. And more popular and understandable to all experts is graphical form of definition, because when you ask any expert in the field of district heating what peak heat load means, usually we start drawing this heat load duration curve, which can be seen on the screen, showing that this peak in the beginning is peak heat load. And another form of definitions available for peak heat load are mathematical equations and using mathematical approach, which is extremely important when you work with modeling and simulation of peak heat load. And the main part of taxonomy is classification or categorization. And we had three big groups of categorization criteria. First group is by duration. So depending of length of when peak heat load occurs, it can be daily or seasonal peaks. And in some cases, frequency is important, how often peak heat load occur, and so revealing patterns and causes. And another group of criteria for classification is related to size of peak heat load. First part is maximum heat load, so with highest heat demand, which is very important for planning and infrastructure optimization. And categorization related to size is related to district heating network. So depending on the size of network, a large, medium, or small scale, it has definitely impact on peak heat load characteristics. And the third group for categorization criteria is a form of profile, because depending on heat demand type, on the age of district, on the situation with heat demand in buildings in a specific district and district heating network. So the profile is different. And the situation with the district where there is the largest part of buildings are nearly energy zero buildings or old buildings are absolutely different heat load curves, and that's why peak heat load is different too. So another part of taxonomy includes related aspects related to peak heat load, and one group of these factors are shaving technologies, like using building thermal mass for short-term heat storage, or demand management and demand management respond with strategies to reduce peak heat load and thermal storage, both short and long-term storage. And another group are impacting factors, which are definitely related to factors that has influence on heat load demand, thus having influence on peak heat load, like weather impact or consumer behavior, and the efficiency and sizing of heat generation units, and for long-term, like extreme climate conditions too. And so the main conclusions related to taxonomy, that these taxonomy analysis gave us possibility to investigate this comprehensive topic and provide this structured analysis via taxonomy. And we identified widely used peak heat load covering technologies and future potential peak heat load covering technologies. And we use these identified technologies for future analysis that will be presented after me. And impacting factors and shaving technologies have been analyzed, and based on it, the possibilities for decarbonization of peak heat load have been identified, and there are two possibilities, which I will tell in the next slide. So first group is peak heat load management, heat demand management, thermal energy storage, and synergy with individual heating solutions. But focus of our research project was on peak heat load covering technologies. So it is very important to make optimization of these covering technologies, both from economical point of view and evaluating key parameters for selection of these technologies, like CO2 neutrality, fast start capability, required size, and minimum heat load and other critical factors. And the main technologies which have been analyzed, and you will see this analysis, are electric boilers, biomass boilers, heat pumps, and in some cases, thermal energy storage. But about it in details, will speak Hesham Ali, our early stage researcher from Tallinn University of Technology. Please, Hesham, floor is yours.
Yeah, thank you, Anna. Hello, everyone. So I'll speak today about the methodology we used in our analysis, and I'll present some key results in the project to identify and estimate the technical feasibility and applicability of some options to cover the peak load in district heating networks. As discussed before, there are like different categories of district heating networks, different sizes, different supply temperatures, and there is no optimal solutions can work everywhere. Each case can be specific and have good solutions for it, different cases. So in our analysis, we started by categorizations of the district heating network according to the size of the district and to the supply temperature. So we categorized 4 different types of district heating networks: large scale high temperature district heating network, a large scale low temperature, small scale high temperature, and the small scale low temperatures. From these 4 categories, we needed to build and construct heat load curves. So we had some data and we monitored some buildings to construct and build the heat load curves for each types of the district heating network. And we built 4 profiles or 4 heat load curves: the large district heating network with 100 megawatt capacity and the small one with 10 megawatt capacities. And the supply temperature was estimated as 90 for the high temperature and 70 for the low temperatures. Then after the categorizations of the district heating network, we needed to develop some scenarios. And the scenarios will be based on the peak load capacities and the technologies to be assessed to cover these peak loads. For each type of the district heating network, we had 3 different scenarios. Specifically, the first one, 10% of the total capacity of the district heating network need to be covered by the peak load units. The second one is 20% of the capacity to be covered by the peak load units. And the third one is 40% of the capacity to be covered by the peak load units. And these 3 scenarios of the peak heat load capacities were applied for the 4 types of district heating network we have. And then for each one, we will assess 4 different technologies. We have the gas boiler, electric boiler, heat pump, and biomass boiler. We took the gas boiler as a reference scenario, where is the unit that can be used to cover the peak load units, and then compare the 3 other technologies to the gas boilers. We see the matrix here on the right. We have the 12 different scenarios: the low temperature and high temperature, the small scale and large scales, and the 3 different scenarios in each type. Next, for each scenarios, we did some technical assessment to compare the technologies, and we evaluated some performance indicators, namely the energy efficiency. We estimated the energy efficiency by the heat output and the primary energy input for each technologies in each scenario. Then we estimated the primary energy saving by comparing the primary energy consumption for the selected technologies compared to the gas boiler. Then we estimate the carbon emission reduction by using the specific technologies here by the heat pump, gas, electric boilers, and biomass boilers. And the last indicator we used is the levelized cost of heat. And the data we used in our analysis, especially when we speak about the electric boilers or heat pumps, are based from the current European primary energy factors and emission factors. So we estimated the average in the European Union, and that can explain like the emission factor in the electric boiler or heat pump. It's the current primary energy factor in the electricity mix in average in Europe. So if it was green, the result will be different, and it's different between regions to another when we speak about the mostly electric technologies. Now I'll present some results. First, the categorizations and scenario analysis and heat load curves. On the right, we see the sorted heat load curves for the 4 district heating network: large scale hot temperature, large scale low temperature, and small scale hot temperature, small scale low temperatures. We can see like the main key out we can take from this curve that the low temperature, which is the efficient network, have a smoother curves, which means like when we have low temperature district heating network, the peak load will occur much less on the different capacities, and we can see it in numbers on the matrix on the left side. For example, for 10% in the high temperature, the occurrence of the peak load will be 38 hours a year, while in the low temperature will be 3 hours. And when the peak load capacity cover 40% of the total capacity, the occurrence of the peak load in the high temperature will be over 1,200 hours, while in the low temperature district heating network, it will be around 100 hours per year. And now we have the hours where the peak load units can be operated and the amount of energy, thermal energy, to be output from the peak load units in the different scenarios we have. Now I'm showing some performance evaluations, mainly the energy and carbon emissions. From the primary energy consumption, we see the 4 technologies: gas boiler, electric boilers, heat pumps, and biomass boilers. In the different scenarios, we notice here the heat pump has the least primary energy consumption due to the COP, which is usually above 1 and higher than other technologies. Then biomass and gas boiler quite close to each other. The electric boiler would consume the highest primary energy consumption in most of the scenarios. For the CO2 emissions, biomass boilers will be the least emissions of the CO2, followed by the heat pump, gas boiler, and then electric boilers. Again, I need to highlight this is from the current electricity mix in Europe. The final conclusion of the analysis, we assessed 4 different technologies: gas boilers, electric boilers, heat pumps, biomass boilers, and the primary energy consumption trends. Heat pump has lowest consumption across all scenarios. Electric boilers consume the most. The CO2 emissions, biomass boilers significantly reduce emissions in all scenarios. Heat pumps can achieve substantial emissions reduction, especially if the COP is high. For example, if it was possible to connect the heat pump with another source of heat. Gas and electric boilers have higher emissions, especially at 40% peak loads. And again, capital cost and operational cost are the main indicators or constraints to use on the peak heat load. And for the financial analysis, next presentation will be by Robert, and he'll speak more details about the financial for each technologies. And yeah, I finished my part. Thank you.
Thank you, Hesham. Hello from my side. I would now talk about the economic analysis we conducted as part of the REPEAK project, where we calculated and compared the levelized cost of heat of different technologies. So one of our main goals was to evaluate different technologies that could provide renewable heat peak load capacity. The technologies considered in this study are biomass plants, electric boilers, heat pumps, and gas boilers with green hydrogen. The economic evaluation was based on the data from two technology catalogs. So one was from the Danish Energy Agency, and the other came from the Energy Agency of Baden-Württemberg. These catalogs gave us information of the investment costs, fixed and variable operating costs, excluding fuel costs, and on the expected lifetime of each technology. To get the reliable fuel costs estimate, we did a literature review focused on sources from within the European Union. The only exception was biomass, wood chips and pellets, where we used Austrian values because there weren't consistent EU-wide values available. We analyzed two scenarios. In the first, 10 megawatts of capacity had to be available from 50, 500, and 1,000 full load hours. In the second, it was the same range of hours, but for 100 megawatts. These numbers came from a survey of district heating experts that we carried out during the project. And in both cases, we assumed that this capacity had to be available at any time. And now I will show you the results. So if you take a look at this graph, you can see that at low full load hours, that is when the systems are only running a few hours per year, you see the results in the dark bars. So electric boilers and gas boilers with green hydrogen came out as more cost effective because of low investment costs. But if as the number of operating hours increases, showing in the light bars, operating and maintenance costs play a much bigger role, and also fuel costs. And that's when biomass plants, for example, start to become more attractive economically. Yeah, as I already mentioned, the investment costs are important or play a significant role for technologies which run just a few hours a year. And we also have some restriction for this analysis. So we used average fuel costs, so we have no consideration of electricity costs at peak load times. And we looked only at technology-specific costs. That means factors like square meter prices, grid connection fees, etc. were not included, but of course they can significantly affect the final results in practice. So I appreciate your interest in our product, and now I want to hand over to my colleague Simon Moser again.
Thank you very much. And I come to the part of the survey which we conducted in our project and the results that we derived from that survey. So let's start with the method. So there was an early version of the questionnaire from a previous project that we refined based on the feedback from experts and also from the consortium members. And it targeted two groups of respondents. The one was district heating networks, and the other one was district heating experts. So networks means that we wanted to know from really different networks what their specific challenge and their specific potential solutions are, and not only from very specific operators. So to say, if one operator has more than one network, it was also possible to get more answers from this one. We conducted the survey and we finally had 153 valid responses after data cleaning, with 70 answers from district heating operators and 83 answers from district heating experts. And both were evaluated and, of course, then compared regarding the answers that they gave. There were some limitations which I want to highlight. First, with 70 or 83 district heating experts, which are also allocated in different countries, etc., there is a limited statistical significance. So you cannot really talk about, significance intervals, etc., but it gives a good interpretation of what the current status is. Also, there is some high share of responses from small Austrian district heating operators. Just to be clear, it's not an absolute high share, but it's a relative high share, meaning that there are significantly more answers from this group, but not really so that everything is totally biased. And having that in mind, I go to the findings that we have. Just some descriptive analysis. This is also very interesting. I think we have responses from networks that provide 600 megawatt hour per year up to 6,000 gigawatt hour per year, meaning that there is a 10,000-fold volume that is distributed, and also the median network is exactly in the middle with 65 gigawatt hours per year. The district heating networks more or less all provide space heating and hot water, also meaning that other uses that could be relevant the whole year round, like process heat or something like that, are really rarely included in the district heating network operators' business models. And for us, that means that peak heat loads are really depending on the weather conditions, the buildings, and the behavior of the customers there. And yes, as mentioned before, not on, for example, some kind of base load process heat profile or something like that. We see that the minimum summer demand is approximately 10% of the maximum winter demand. And also with the statement, this is very related to some findings about peak loads. We see a maximum supply temperature in winter on average between the networks of 100 degrees, and an average return temperature, again in average over all the networks, of 45 degrees. Also, 60% of the responding district heating networks have a central storage. And I think also this is very interesting because the larger the network is, the more likely it is to have a storage. But on the other hand, we also see that storage sizes decrease in relation. So the larger the network is compared to the size of the network, the smaller is the storage that the network has. Then we asked about the current provision of peak heat loads and what the peak heat load units are. And it was a multiple choice question. More than one choice was possible. So we put up the hypothesis that peak heat loads are predominantly covered by fossil fuels, and this hypothesis is proven because we see that also in district heating networks that already heavily rely on CO2 neutral supply units, there are fossil boilers, there are which are used for backups, which are used for some minor percentage point, of course, but still the statement is that these are fossil units that are active, and so this hypothesis can be verified. Thermal energy storage and preheating the networks are common measures. So the district heating operators as well as the experts state this in their responses. So we have also asked what the challenge of peak heat loads is. How much do you need to decarbonize? How much energy is it? How much megawatt is it? And therefore, we wanted to have a clear insight in the district heating operators or district heating experts definition. And this is very interesting because it is more or less directly connected what Taltech found out about the different ways of defining peak heat loads. It is exactly also the case here because we see that peak heat load can be defined about a certain period or with regard to exceeding a certain threshold. So there is not a clear definition, but it is more or less divided into two parts if you quickly ask someone to respond to the question of definition. Nevertheless, that does not mean that there is not clarity in the specific case. So I guess whenever experts, researchers, etc., talk about their so to say own peak heat load, I think they definitely understand each other. And what we also see or asked is when does the peak heat load time occur? And we see that there are more or less two different types, which is the peak load that occurs for some hours, which especially is in the winter mornings or also the winter evenings. And on the other hand, when there is longer term harsh weather for some days or weeks, so to say a time period that is longer, where it is really actually cold in comparison to the rest of the year. And therefore, we also asked how long is the duration in your network, and we see responses ranging from as little as 10 hours to up to 1,250 hours per year. We see a median value of 200 hours and a mean value of 350 hours per year, which is defined as peak heat load by district heating operators. And the next thing was to ask what do the district heating operators expect in their network to be the peak heat load unit that is applied in a net zero situation. And again, multiple choices were allowed. And as you can see on the left side, there is yes, there is a winner, but there is not such a clear winner. It is more or less distributed among very many options. And we see that, yes, on the one hand, there is this wide distribution, and also that the district heating operators and also the experts choose more than one technology very often. So they combine technologies in order to provide peak heat loads. Thermal energy storage is the most mentioned option. It is the one ticked the most time, but of course more or less exclusively in combination, most often with heat pumps. Meaning that, of course, it needs kind of a generation unit, as the thermal energy storage, of course, is a peak load unit maybe, but it's not a generation unit itself. And you can see that there is the electric boilers, the heat pumps, the biomass boilers, and the green gas boilers, which are elsewise mentioned most often. We also asked if district heating networks do have a decarbonization strategy on the one hand, and then if this decarbonization strategy actually includes peak heat loads, or is it only limited to starting at the base load level. And we see three things. First, approximately half of the networks have a net zero strategy. we see that there is no correlation with the size of the network. So decarbonization strategy does not depend on the size. It can be some small planning maybe for a smaller network and some big planning for a bigger network, but the distribution of strategies is not really focused on the size of the network. And we also see that if they have a strategy, these do include peak heat load provision, which also means that we have to reject the hypothesis that this is not the case. What are the disadvantages of the net zero choices? We asked to rate for their specific options. So this is not for some technology, but this is what a rating for what the district heating operators said that this is their choice. And we see that definitely any choice is an expensive investment. The capex in comparison to the volume of energy that is provided remain very high. And we see this as a proof, so to say, that capex is really the problem of transitioning peak heat loads. And we also see that OPEX are a topic that probably means that fuel costs can be high for the short duration that the units are run in the year. Nevertheless, of course, high OPEX, high fuel costs mean high OPEX, and therefore they remain a challenge. And what we also see, and maybe this is one of the most interesting things from my perspective, that the district heating operators, when they do have a strategy, they really take those opportunities that exist and that are proven technologies. They seldomly rely on something like hydrogen or carbon capture units, etc. On the contrary, district heating experts tend to believe in these future developments, so they rely on green gas or demand-side management definitely more often than the experts do, than the operators do, sorry. Yes, also regarding the duration and the capex that are allowed for the peak heat load units, we see that heat pumps, which are more efficient than electric boilers, but are definitely also more expensive. And we also see that CHP plants, which are a high exergy unit, meaning that they convert the gas or the oil or etc. to electricity, and only use the heat as a residue. They are both more or less chosen less often because the experts and district heating operators, or the experts in this case, think that the unit is around 2 little hours per year in order to justify these capex investment. And therefore I come to the conclusions of our study, summarizing all the findings that have been presented very briefly. We see that the definition of peak heat loads in district heating network remains intangible. We see that it is not a one definition and that it's not clear, but on the other hand, yes, there probably is some consensus in any talk you have to each other what is currently meant in the specific case. In most cases today, peak heat loads are provided by fossil-based units. We can verify this hypothesis. Peak heat loads are in the focus of district heating operator strategies. We see that the high investment costs are necessary for the transition and the transition of peak heat loads, and that district heating operators plan with existing and proven technologies. Thermal energy storage, electric boilers, heat pumps, biomass boilers, and green gas, green oil boilers are the most mentioned options. But to be clear, green gas boilers are not a dominant option in comparison to the others. And hydrogen and carbon capture are hardly mentioned, meaning again that we need to reject this hypothesis that this is more or less the future benchmark. No, on the contrary, it's one solution that is in consideration among many others. Generalizing combining systems is repeatedly suggested. So this is really, if you look at the answers also individually, there are very often combinations of kind of upper peak heat loads. When you look at the load duration curve and lower peak heat loads, the experts and operators are talking about diversification, are talking about reserve. So combining remains a big topic. And one central sentence also in the answers is that thermal energy storage is the basis for the peak heat load system. It enables a lot of different technologies. It makes the duration of peak heat loads even longer, so to say, or you can use more efficient technologies like CHP, like heat pumps, together with the thermal energy storage. Nevertheless, to be clear, when you read these answers, it is rather clear that experts refer to buffer units, meaning that these are thermal energy storages for some hours or even for some days, maybe a week, but that's already very long. So they are hardly talking about seasonal storage systems. And also, in comparison, experts and operators, the experts are repeatedly referring to the potential of demand-side management, which they see as a more cost-effective option, and also want to highlight this in the results to make also the operators more aware of this option. Yes, as mentioned before, there were many answers, and we have tried to bring them all together and to combine them wherever possible in a SWOT-like matrix. That means we did not do the 2x2 matrix, but in order to have a good overview, we listed the individual options at the left side and put in the strengths, weaknesses, opportunities, and threats on the horizontal axis. And there we put all the 188 pros and cons that we found for the 12 selected peak heat load options. And for that, I can only say stay tuned for the final report, which again is in the IADHC for final approval. Thank you very much for the team and my side. Thank you very much.
Thank you, Simon. Thank you also, Robert, Anna, Hesham, for your presentation. I think was a great overview of the project, the study being done there. So now, to continue with our webinar, I am going to invite to present the representatives from Linz AG that will talk a little bit more about a concrete case of peak heat load demand control, and they will talk about the case in Linz. And for this, I have here Simon Glaser and Melanie Hortler. Simon, he's been working as an asset manager for the Linz power plants for the past 4 years, and his core responsibilities include industrial waste heat utilization and the expansion of the energy portfolio within the city of Linz. Melanie has a master's in renewable energy systems and technical energy management. She currently works as an expert for strategy, research funding, and public affairs at Linz AG. So to talk more about this concrete case in Austria, the floor is all yours. Thank you.
Thank you very much, Ivan. Hello and a warm welcome from all of us here at Linz AG. Melanie and I are asset managers in the energy conversion department in Linz, and we are pleased to contribute to the REPEAK research project and share our insights as a local energy provider. The agenda. First, I will speak about the district heating system in Linz and about our current heat peak load situation. Then I will focus on our existing district heating storage, and I will focus about the thermal power unit. So it already helps us now for the peak loads. And last, my colleague Melanie Hörtler, she will talk about the renewable world and the future projects. So this is Linz. Linz is an industry city in Upper Austria with a very high energy demand in a compact area. These are ideal conditions for us as a district heating operator. We supply heat around 84,000 households across Linz, Leonding and Traun, providing approximately 1,300 gigawatt hours of heat per year. This gives us one of the highest district heating connection densities in Europe. Our generation we have on two sides. So you see here the side Mitte, Plant Mitte, and here you see the Plant Süd. So in the Plant Mitte we have, of course, gas CHPs, we have gas boilers, we have a waste incineration plant and a biomass plant, and a thermal storage. On the Plant Süd we also have gas CHPs. Across both power plants, 63% of the heat is generated meanwhile by gas, and 25% is residues, and 12% are biomass. And and here it's like, let's see how we currently handle our heat peak loads. When there is, example, a cold winter day, we need a power generation of 500 megawatts by minus 10 degrees. To be able to supply this 500 megawatts thermal power for our district heating network, we have different plants. So the first two bullet points is the gas CHP. So therefore we have extraction of condensing and back pressure turbine, Mitte, and the same in Süd. So if we bypass the steam turbine, we have a little bit higher thermal power, as you can see. Then, of course, we have gas boilers with 120 megawatts. We have waste incineration plant and the biomass together 65 megawatts. And our thermal energy storage, if we look about the power unit, it's between 0 and 120 megawatts with a temperature of 97 degrees. So these assets we have, but we also have to ask ourselves the question when it comes to heat peak loads, how do we operate our power plants? So if you do the math, you will see that we have more than enough thermal power to reach the 500 megawatts. So in order to see how we operate our power plants, we need to look at economic factors too. And therefore, the clean spark spread is a key indicator for our gas CHPs, for example. But we also almost have to keep in mind that we have the obligation to keep the city warm. I made here this simple graphic. On the top of this blue line, you see the electricity side, and on the bottom, the heat side. So this is a little bit how an energy supply company like we think. We always have a market price for electricity, and all power plants need fuel, and we are in the ETS, so we have to pay also the carbon price. And what's in between is the clean spark spread. The clean spark spread is then the indicator how we run our CHPs. So, but the clean spark spread can also be 0, or it can be also negative. And then, of course, the district heating revenue is also really important. So, but I leave it up here to the economic experts, this graphic, and maybe we can discuss about it later. Good. Then now I will focus about a tool we have who already helps us for the heat peak loads, and it's our district heating storage. And I will focus, as I said, about the thermal power unit. So some facts. Our open storage has a height of 65 meters and a diameter of 26 meters. It stores a volume of 34,500 cubic meters, with a temperature of 97 degrees. This results an energy content of approximately 1,400 megawatt hours. So, but we also have some another advantages because of this storage. So it's possible now that we have an extremely stable pressure maintenance, also the expansion compensation of the district heating water, and we also have higher fuel utilization through our back pressure steam turbines. Also the constant return pressure or the feed water replenishment are another benefits. But most importantly, and now also when it comes to heat peak loads, it saves the runtime, the storage of our heat peak load boilers, as Simon said before, and also Lars talked about it. And this is also a really big advantages. And therefore, I will go now a little bit more into detail. And here I wrote the formula about thermal power. So Q point is equal the mass flow multiplied by the specific heat and multiplied by the temperature difference. So the temperature difference is somehow locked because in our thermal open storage, we are limited with the atmosphere, so we cannot go above 100 degrees. But the return, we could go lower. But that's a very long story. I think a lot of experts, the district heating return, how we will get this lower. This is a long story. I will not focus now about it. The specific heat capacity, I think it will also be water in the next years in our district heating systems. So it's also locked somehow. And the mass flow, it's our own real variable we have. And this is always depending on the dimension to the storage, but also about the network. You also have to bring the water into the power plants and also out. That's also the thing with the mass flow. So, and this power between 0 and 120 megawatts helps us currently already for the peak loads. And now I go a little bit more into detail. We see here now the energy of our storage. And on the y-axis, you see the megawatt hours. So on Monday in the morning, our storage level is on its minimum in 8 in the morning. And under the day, we charge the storage. So at and this every day till Friday. Till Friday at 8 o'clock, the storage is on its highest energy level. And on weekends, we discharge it again. Only on holiday, as you see here, Feiertage, this is example Christmas, 24th of December. There it's we do it in a different way. And why is that so? And therefore the thermal power, as I said before, is really important. So now on the y-axis, we have the power. And we always charge, mostly during the day and on weekends, when the clean spark spread is high. The clean spark spread is high. Then, of course, our CHPs are running and we have a lot of cheap heat, let's say. So we charge our storage. We discharge the storage when the clean spark spread is low. Example, as I said before, at Christmas. So the companies are closed. There is most of the time no spread. So our fossil power plants are not running so much. So we are happy to have the energy from the storage. So there we discharge. Yeah, that's it so far from the fossil world. And now I will hand over to Melanie Hörtler, my colleague in the asset management, and she will speak now about the renewable world. And I think this is now a little bit the fossil world, but we also can learn something from it. So efficiency will be also in the renewable world more and more important, even when we look at the fuel prices in the future, like H2, biomethane. Yeah, please, Melanie, I do give you the future projects.
Also from me, a warm welcome to today's webinar. The research project Heat Rock Storing Heat Inside a Mountain. As a part of an innovative research initiative, a multidisciplinary team of energy experts is exploring new ways to support the energy transition. The Heat Rock project tackles a central question. Can hot water be stored inside a mountain? And can it be used in winter to supply district heating? The core idea is to store renewable energy in summer and use it in winter, as we all know, a key challenge of the energy transition. The project investigates a forward-looking approach using underground caverns as a large-scale thermal storage to decouple energy production and heat demand over the time. Our vision as Linz AG in this context, we see great potential in a cavern storage system with a volume of 1 or 2 million cubic meters of hot water. If it's operated at the same temperature level as our current steel tank, which were Simon talking before, this would offer a thermal capacity of around 70 gigawatt hours. On very cold days, for example, by minus 10 degrees, our total heat demand can reach up to 500 megawatt. With the planned cavern, we aim for a discharge power of 300 megawatt, which would be a significant contribution to our district heating system. The key benefits of a large-scale thermal storage absorbs surplus renewable heat during high production periods and releases it when the demand is high. This prevents curtailment and enables peak shaving. It also allows flexible use of industrial waste heat, which often doesn't match demand times. Stored waste heat can be fed into the district heating system when needed, so it's reducing reliance on fossil peak boilers. By shifting heat feed in over time, storage improves network efficiency, storage lowers fuel use and CO2 emissions, and it stabilizes the system. So, the next slide, please. I want to say something about future projects. Oh, sorry. Thank you. At Linz AG, we aim to reduce our dependency on natural gas and make our heating system more flexible and climate friendly. I will talk about 3 key technologies which could support this transition and enable effective peak shaving. The 3 technologies are power to heat, biomethane, and hydrogen. However, any transition must be economically viable and affordable for our customers. Only then will a real system change for us as an energy supplier be possible. So power to heat, with this technology, excess renewable electricity is converted into heat by using, for example, electrode boilers or heat pumps. This enables peak shaving, relieves the power grid, and supports sector coupling. The key challenges are here, of course, the high electricity demand, grid capacity, and economic viability depending on electricity prices. Then the biomethane. It enables low emission peak shaving in existing gas system without any technical changes or not many technical changes. It offers flexibility, but the availability is limited and it competes with other sectors. So the key factors are the costs and the supply. As already mentioned, hydrogen enables CO2-free peak shaving with fast, flexible capacity and H2-ready systems. Very high cost, and we would need a new infrastructure. Our peak load strategy to sustainably manage future heat peaks, we rely on a smart mix of technologies that reduce fossil-based generation while ensuring affordability and reliability. The key actions include using thermal storage to smooth loads, combining power to heat with biomethane and hydrogen for flexible peak coverage, and applying intelligent control system. So to sum up in a nutshell, power to heat enables low cost, short-term peak shaving. Biomethane works well in existing gas systems, and hydrogen offers a long-term zero-emission option. Linz AG is contributing to a European flagship research project at the moment to further explore hydrogen's role in this strategy. The name is EU H2 Stars. Linz AG is a key partner, and the initiative is to store green hydrogen underground and use it seasonally for heat and electricity. Our role is here, or the key role is here, to assessing the integration of hydrogen into one of our CHP power plants. I hope I was able to give you a brief and an interesting insight into our topics in the practice. And now I would like to give the floor to the next presenter.
Okay, thank you so much, Melanie and Simon, for your presentation. Talking a little bit more about the project and the concrete case in Linz, in Austria. And now we're going to talk a little bit about the policy aspects. What policy recommendations the project has that can help improve a faster uptake of decarbonized options for peak heat load. For this, I'll give the floor to my colleague, Victoria Lienar, which is a policy advisor at Euroheat Power. She also has an academic background in law and political science and has an expertise in climate policy and industrial emissions. Her work focuses on key regulatory frameworks, such as the EU climate law, the emission trading system, and the industrial emissions directive. So from the conclusions, from the results of the project, we drew up some policy recommendations that will also be made available shortly in social media, but also on our website. But Victoria will briefly talk about these recommendations based on what we studied at REPEAK project. Victoria, the floor is yours.
Hi everyone, and can you hear me properly? Yes?
Yes, we can.
Hi everyone, and good morning. Thank you, Evan, for the presentation. So yes, indeed, as you said, I will present the policy recommendation based on the REPEAK study, but not only. So some recommendation are also based on more specific understanding of the heating and cooling management at the EU level. And we will, for this context, what I will present now, it's not really part of the study, but will be in a booklet that we are currently preparing and that we will distribute to policymakers and utilities to help them really tackle this issue. So I think I should have a control. Yeah, perfect. So our first recommendation is to establish a standardized definition and reporting framework for peak heat load. So this idea directly derives of the taxonomy of peak load definition and influencing factors work that was done by the researcher of the study. And the idea so is to share it as much as possible. So as it was unveiled in the webinar earlier, it reveals that there is a widespread lack of consistency in how peak heat load is defined and measures across the DHC sectors. Here you can read some specific data, and this inconsistency really hampers the comparability of data. It also obscures the scale of decarbonization challenge and complicate planning, benchmarking, and policy evaluation. So our recommendation is, as Simon says, also it's rather than imposing one rigid definition, it's to recommend to use this taxonomy, and that actually reflects the complexity of real-world DHC system and offering also a common language. So the idea is, of course, to embed this taxonomy into national and EU statistic, emission reporting and planning templates. It can also be used to require the use of key performance indicator. That would be really important to actually help to describe each situation, specifically because the heat load is peak heat load is not the same depending of the size of the plant, etc. So you can, for example, use it. An example of KPI could be the the peak to base load ratio, annual peak load duration, CO2 intensity of peak heat supply, etc. So these are examples. But yes, of course, this use a taxonomy to harmonize all of this across also researcher, etc. So this is will be done based also on the booklet that we will spread, and yeah, so policymakers can use it as well. And after implement this in more structured policy support. For our next, so our next recommendation is to prioritize thermal energy storage as a strategic peak shaving solution. So according to the study, TESS is rated as by DHC expert as the most promising and widely applicable solution as a standalone solution, but also as a key enabler in combined low carbon systems. So here the advantages are plenty. I'm just mentioning some of them is the increased system flexibility, smooth load profile. It reduces dependency on fossil fuel peak boilers and also enhance overall efficiency and reduce operational costs. So as you can see, it can be in a more complex system. You can see it on the graph here, where TESS can be in the middle. Here you have an heat pump that is included, but it's one of the technology that can be combined. But the problem is that despite all of these advantages, you can it still has a high upfront costs and limited space in cities. So DHC systems are most efficient in high density urban areas. So that's also, of course, the question of limited space. So you can have a thermal storage in the form of a tank, but also of a pit storage, for example. And this really requires some organization. So our recommendation here are, of course, government and funding bodies should prioritize TESS in public funding scheme. So, for example, offering capital grants, low interest loan, and technical assistance. This is especially for small and medium-sized DHC networks, because as Simon says, the larger the DHC plant is, the more likely it is to already have this kind of solution. To tackle the space issue, local authorities should, for example, incorporate TESS infrastructure into urban zoning, energy planning, permitting framework. And at AU level, what we can mention, and this will be also part of another recommendation, is if you want to have concrete support and action, the deployment of TESS could be, for example, incorporated in upcoming legislation. So, for example, the Electrification Action Plan and the European Grid Package that are currently under discussion. They are both under consultation at the moment and should be released the beginning of next year. So this would be a good point for advocacy here. So our third point is to tackle investment barrier for CO2 neutral peak heat technology. As I mentioned, it is the case for TESS, but not only. And we also mentioned heat pump, renewable fuel boilers, etc. And it was shown that high capex is the main barrier to this adoption. We see, for example, the problem is to recover the cost for such a small period. It's less efficient, and fossil fuel boiler remain dominant not because of their efficiency, but because of this high upfront costs and the quick payback of it. Also in the survey, I don't want to mention everything, but two-thirds of the experts says that it's more likely that DHC operator will go for a less efficient solution because of this specific issue. So here, not all recommendations are about money, but here indeed it really makes sense to introduce target capex grants and low interest loan for renewable assets. And it could be one of the additional conditions for this capex could be for this grants and low interest loan could be to, for example, systematically analyze the possibility of combining with thermal energy storage. So For the fourth measure, we want to encourage combined solution and system integration. So the REPEAK study here really shows that decarbonization of peak heat supply is most successful with multiple CO2 neutral technology and are combined in a system integrated approach. So this is really this multi-technology configuration that we are talking about. We find example in the studies such as test plus heat pump or electric boilers and green gas. So this is a typical example of what I said. This is not directly part of the study, but we know this is working for to encourage this type of system integration. Is for example a reform of tariff structure and compensation mechanism. So we know that in some countries it's already a normal case to have a dynamic electricity tariff, but it's not always the case. So this will encourage GCO operator to run electric boilers and heat pump during period of high renewable generation and low market prices. Also, you can provide support for DHC grid development and refurbishment. So national and regional government could establish dedicated heat transition fund that offer a grant or low interest loan for modernization and expansion of integrated low carbon infrastructure. This can be prioritized for modular and scalable projects. And this targeted financial support will help de-risking investment also and accelerating this implementation of such measure. Also to ensure this more resilient and efficient energy system, one of the main points that we actually notice is really to help have a better integration of electricity and heat planning. So a more collaboration with DSOs and TSOs. This is already seen in the renewable energy directive and the energy efficiency directive, but this is not really spread yet, and there are not much guidance or business model on how to actually do it. As building, for example, a pit storage takes some years to implement, but you also need to collaborate with the DSOs to bring the grid there. So it takes up to 5 years to this kind of projects, and this really slower down this move. And yes, this system integration criteria should be embedded in spatial planning and project permitting in general. So the last point is to support knowledge transfers and capacity building. As it was said, it's small and medium-sized DHC operators often lack of technical expertise in planning tools. And the tools that are available make it hard to evaluate. So many operators struggle to assess trade-off and system performance in this. And they need also to compare technology. What we saw a bit earlier in the presentation is that there is no one-size fit for all solution. They evaluate it. Of course, it depends on the type of the peak and the hours, which technology would be more cost efficient, etc. But in general, there is a very nice SWOT that was developed, and we truly believe that the more this SWOT is shared, the better it will be, because it will really serve as a good decision-making tool depending of each specific type of plan. So this will all be in our booklets, and we will try to spread the message as much as possible in the text. So voilà, thanks a lot.
Thank you so much, Victoria. Yes, the booklet will be available soon. So we're finishing some details, but soon everyone will be able to see all these policy recommendations in more in-depth. And without further ado, I actually go to the other concrete case study, this time in Estonia. And presenting will be Eduard Latosov from Utilitas, and he's a thermal engineer with extensive practical experience. He's an author of 40 scientific publications and has been the principal investigator of many scientific and research and development projects. So before giving the floor to Edward, I remember everyone, you are more than welcome to send your questions and your comments on the Q&A box. All these questions and comments will be answered by the end of all of the presentation, so after this one, and then we can discuss and exchange some ideas regarding peak heat loads. So now I give the floor to Edward.
Thank you for introduction. So I'm working in Utilitas, and Utilitas is a leading producer of renewable heat and electricity in Estonia. We also acting in Latvia and in Lithuania. And you can find on the left side the main, major our outputs. So amount of employees, amount of heat produced, and electricity produced the previous year. So here you can find some locations where we have district heating in Estonia. And 5 of them, Haapsalu, Vigeva, Rapla, Valga, Keila, in this black box. In those locations, heat demand is around 25 up to 60,000 megawatt hours, rather small locations. And they are quite the same. We have one biomass boiler there, plus natural gas or some kind of a fuel oil or peaks. Tallinn is a large city, is a little bit different. I will speak about that later. And Kerala, the last one, is there we have the same option, one biomass boiler plus fuel oil. But this, in this location, we are not operating during the summertime, so we don't produce heat, and that's why the share of renewables is quite high, 99.9%. In other locations, we have something to improve. So this is the classical shape of in those 5 regions, in rather small regions. So you can find summer load. The black or the gray one is the natural gas or fuel oil. During boiler maintenance or extremely low heat load demand, we are not running biomass boilers. We can't run them. So we are using natural gas or fuel oil. The second place is here, the peaks. So we can't cover the peaks. We using the fossils as well. And there are also some drops during the intermediate lows. So we should maintain the boilers. We should clean them up. And we have also drops in renewable heat production as well. So what we can do and what we are, what we have in our solution pool. The first one, of course, is heat storage. So we can put heat storage, we can cover the peak loads. That's why not. It seems to be okay. But we have problem during the summertime. So why I'm showing or telling about that, because sometimes solutions, especially in the small district heating regions, which can help in peak loads, can also help during the low load periods as well, in some of them. The second option, what we can do, we can install second stage flue gas condenser. We can increase heat output from the boiler using the flue gas condenser. We can cover with peaks in additional heat storage, but in this case, heat storage will be not so huge in comparison to solution without second stage flue gas condenser. But the problem with summer load is still there. But what we can be solved, we can also install air to water heat pump to run during the summertime, and combination with heat storage is perfect. So heat pump COP is quite high during the summertime, and in combination with heat storage, we can run, as an example, during the nighttime where electricity price is lower, pump it to the heat storage and optimize the heat price for the consumers in this way. This is one of the solutions. And I want to show you the IGEVA. This is one of our district heating network, and we are really working on air to water heat pump plus heat storage solution. So right now the heat pump building is under construction. Heat pumps will be delivered on the site at the end of this week, and the construction of heat storage will start also at the end of this week. So this is not a theoretical solution, this is a real solution which will be implemented in the city of Igala. There is also in option number 4, which is not probably widely discussed here. We can always add additional biomass boiler, and in this case, we can, with the smaller biomass boiler, we can in this case cover the summer lows, we can cover the peaks. So the classical solution in Estonian district heating networks is to use 2 biomass boilers, smaller and the larger one. In this combination works quite well. But at the end, the option feasibility, there is a strong impact on national investment grants. So we had grants for heat storages, we had grants for heat pumps, and that's why we selected the option with heat storage plus heat pump for Igala. Without those subsidies, I think the option 4 additional biomass boiler will be the priority number 1. So the grants has a significant impact on solutions. Now I want to switch to large district heating grid, the Tallinn. So you can find the distribution different heat production units. The base load, so the bottom is covered by waste incineration plants. Then we have 1 to 3 CHP plants around the city, and the blue one is the gas or fuel oil. So what we can do, or what we're doing to reduce the peaks. The first one is the wastewater and seawater heat pump. It's under construction and will be in operation in December 2026. So the heat pumps will come from Fleotherm. The contract is signed already, and the construction works are in progress. This heat pump will be able to produce 110 megawatts. So it will cover a significant amount of gas. And after implementation of this project, there will be something like 10% left. So we should do something with those 10% in the future. So what other option we have? We have option the heat storage. So 1 is already under construction, 20,000 cubic meters. 2 are under development. So the tender will be started soon. We are also working on peak shaving in buildings to reduce the peaks. So multi-tariff schemes to be introduced soon in our networks. So we are also working a lot on reduction of heat losses in district heating networks, so we can also reduce the peaks by that, so we can reduce the heat losses in district heating network. The 4th is the power to heat. So we have already some electrical boilers installed, and we are planning to install around 100 megawatts of additional electrical capacities. And the final, what we can do, there's a biomass certificate. So we have a boilers. Why not to buy some kind of certificates? I should say, and this is a good option to utilize existing gas boilers. And we have also installed hydrogen production unit near the CHP plant, but I think it's not a big load business. This is something like optimization of existing production units, not the big one. And probably the final idea is this, the large systems become more complicated. So we have a lot of production units, and we should optimize the production. And that's why this is important. I think we cannot work in Excel anymore. So we can buy some smart programs to run this complex system, to take different inputs and provide an operational output. So thank you. That's all from my side.
Thank you so much, Edward, for talking about the cases in Estonia. So we still have some 10 minutes left of our webinar, and of course, I will open up to the questions. We have one question. I think it's an open, so all the speakers are welcome to come forward and answer it. And the question says, from Connie, how can training programs for system operators or local planners be designed to support advanced load forecasting, thermal storage integration, or demand-side management? And how can digital skills development support better management of peak heat loads in the DHC systems? Any of these speakers like to come forward and try to answer this question? So I think we're gonna come back to this question a little bit later. Yes?
Maybe some words. We have some projects. It's a big topic in the company Linz AG. Often we start now with the data. So we need the data first, and there we have some projects running for the data. Example by our district heating storage. If we charge or discharge, the energy management always tells us, because it's depending on a lot of framework conditions. Also, as I told before about the spreads, and then we see in the power plant after the energy management how much is possible in a technical way, and therefore we try always to make the best program. But I think the thing is the resolution. So now the resolution is still not high enough, and artificial intelligence and more data would help us, or also clearer prognosis would help us to do it in a better way. But I'm not therefore an expert. It's more by the energy management.
Okay, thank you, Simon. Question actually to you, Simon, that you mentioned that most of the heat produced currently at Linz AG comes from natural gas, correct? And of course, there's a plan of transitioning to renewable sources and waste heat. So my question is, in any way, is this like change from fossil to renewables affecting the way you manage peak heat loads? And if yes, how is it affecting it?
I think, yeah, it will affect it. So the plan is now we have our base. Now the problem is now also still a part of our base load is because of the gas CHPs, and this is not the optimum. And so that, like Melanie example said, also the strategy in Linz, we have a lot of industrial waste heat, and also when we get waste heat, we put the level up. So if we example, let's say a number, we get 30 megawatts of industrial waste heat with a temperature level, let's say 120 degrees, or with a high exergy, let's say, then we need also less runtime of our heat peak load boilers. So it's sometimes I often hear like also the base load can reduce the heat peak loads. And I think in Linz, example, we have a lot of industrial waste heat, and to make the base load higher with the waste heat in a combination with a storage, the best way would be the heat rock, as Melanie said. We would have a lot of flexibility versions, and maybe the goal should be to need as less hydrogen for the district heating as possible, just for the district heating. Let's say this should be the goal, yeah, in the future.
Yes, thank you so much. I have a question also for Edward. You mentioned, Edward, that you are installing at the Jõgeva power plant. Sorry for my Estonian. But it got me curious, taking all the considerations in the project, repeat when we discussed the pros and cons of each technology, what were the pros that you considered for choosing heat pump installation in that specific power plant? And why was this cost effective in the end of the day?
So all options fits with our main requirement. So to be CO2 neutral, this is what we want. All options are okay. But without grants, they are extremely close in terms of heat production costs. So they are really close, at least in Estonian conditions, so taking into account the biomass price and electricity price, extremely close. So the main decision was based on the price, so the grants. Without those grants, probably the second biomass boiler, in addition to 16 boiler, is more say feasible in terms of economics. So probably I will quickly remind that in Estonia we have authority which so say calculates the price. So the main idea, we are not making classical business. So our price is based on buck weight average capital cost. So our point is to achieve our goals, but make the heat as cheap as possible to the consumer. So that was the main idea. And this combo seems to be quite nice.
Okay, thank you so much, Edward. I see here there are no other questions. So if there are no comments or questions, I think we are good. All presentations were done. And this was the REPEAK final webinar. Once again, I remind everyone that the recording of this webinar and the presentations will be available later. The recording at the Euroheat Power YouTube channel. And for those present, we will send you later by email all the presentations from the speaker, so you can go through again the presentations. And if you have any questions, feel free also to contact them. If there are no other comments, I would like to thank you, all of the speakers, our guests, Simon Glaser, Edward, talking about the cases in Austria and Estonia. I thank you to Melanie also. She had to leave a little bit earlier, but thank you to Melanie also. And our partners at REPEAK from JKU, Robert and Simon, and from Toltec, Anna and Hesham. I think it was an amazing project with some great results. And soon we're gonna have available the booklet with policy recommendations and the final conclusions, the report with final conclusions of the project. And thank you also for the events team at the Euroheat Power for organizing this webinar. Behind the cameras, they're doing a great job. And I say thank you once again to everyone watching us, and have a wonderful week ahead. Thank you and bye.
Thank you for
Thank
the
you, everyone.
organization and for all the speeches. Thank you. Bye.
Bye.
Thank you very much. Bye.